Good day, everybody, and you're most welcome to today's presentation of the CNPS. This is one of these so-called alternative sessions that we hold fortnightly on very specific matters related to fundamental physics, questioning the whole basis of modern physics. Now, today, my name is Ian Cowan from Dublin, Ireland. And I'm hosting these sessions every 2 weeks. Now, today we have Harvey Scribner, who's an occasional participant actually in our conferences, our Saturday conferences. And he has actually given us brief presentations before, I think maybe during the Q&A sessions of other talks. But today we're delighted that Harvey has agreed to give us a full presentation. And what he's done, actually, he's been looking at the works of the late Edward Dowdy in regard to the extinction shift principle. And the presentation is actually entitled Transverse Relative Time Shift. So he's looking at, a moving observer relative to a stationary clock, if you like. And whether the delta t, which is the proper time period in the frame of the clock itself, differs from delta t prime in the observer's period of the clock, whether that would be greater, for example, or not. And he says that two examples from special relativity will be examined: the light clock at rest, and also the light clock number 2 at rest, but with the moving observer. And then the observation is proposed that SR time dilation is actually a 2-signal time delay theory. Now, I'm glad he's going to be explaining that in more detail, because he has mentioned it once or twice when we've just had brief discussions around other talks. But Harvey will be going into that in detail today. And of course, finally, as I say, he will show how to appreciate Edward Dowdy's extinction shift principle, in particular the transverse relative time shift. So, as usual, we have at least an hour available for the talk. Now, there is a possibility of going much further. If there's an hour, we have an hour for discussion subsequently. If there's, say, an hour and 20 minutes, well then we have 40 minutes for Q&A. So there's no problem in over reaching the 1 hour time. We have obviously our people on the social media, the Facebook and the YouTube, and the comments are coming in. You normally have a very healthy discussion, which is fine. That's part of the proceedings. But I'll try to keep an eye on those in case there are any very specific questions which we have to address to Harvey later. Harvey, and I've agreed this with him, it's rational, will not really be looking at those because he won't be able to give a presentation and look at all the myriad of comments coming in, but I'll try to capture any of those which are specific. And indeed, we also have people in the green room. Actually, when we started a moment ago, there were not many people, but I think a couple of them have come in now. So we have more people in the green room, yes. And there's one other thing actually that Harvey pointed out to me, that he's endeavoring to indicate what the ideas of the late Ed Dowdy are and were. And he will be able to speak authoritatively on his interpretation and indeed on his own work following that. But if there are specific questions with regard to the more general or philosophical aspect of Dowdy's thinking, Harvey himself might not be more in the know than any of us, so we might be speculating a bit. And he actually says he's quite happy for anybody else to butt in. I know some people like Harry Ricker and some others have studied Dowdy's work, and if they want to come in and say, no, we think he didn't say this, he said something else, Harvey's quite happy to do that during the Q&A. So we'll start now. Harvey has quite a number of slides, and we'll hand the floor over to him. And I'll just stay on for a moment while the slides are up, and we make sure that everything is working, and you can hear him. So I'll put the slides up now.
Okay, this is. Can you hear me? This is Harvey
I can
Scribner.
hear you perfectly. I'm going to remove myself now, but if you have any question, I will come back.
Okay, thank you. Yes, I'm Harvey Scribner. I had a couple of conversations with Edward Dowdy, and I do miss him. Anyway, okay, so the first part of my presentation, I actually have the order kind of upside down. I'm really going to talk in the beginning about Einstein's time dilation, and then I'll give the examples, and then I'll move towards what I think is a more appropriate view of deriving the similar equation for that people typically use for Einstein's special relativity time dilation, but it's really not. I'll show you. You'll understand when we get there. Thank you for your patience. So, okay, for some reason, I'm unable to advance the slide. Okay, there we go. So the objective is to show how special relativity time dilation is a time delay theory where the light sources are fixed in space and not moving. The constancy of the speed of light has the only solution where velocity of the source is where v equals 0. Another thing I would like to show why the moving source in special relativity is what I believe an illusion. And also then introduce one aspect of Dr. Dowdy's work, and that is the extinction shift principle as it relates to transverse relative time shift, where the speed of light is additive with the velocity of the source. So this is an outline of the presentation. So I'm going to talk about time dilation. Now, I do want to let everybody be clear in the beginning here that I'm not an expert in special relativity as far as the papers and understanding and the evolution of it from Einstein's perspective. What I did in this presentation was something that I just observed when I was reading it on Wikipedia. I'm going to take their example. So this may be a little different approach than what you may be used to, but I hope I can express the ideas and thoughts that I'm thinking clearly enough. So I want to answer the question from looking at the time dilation Wikipedia example. Is the moving observer's period of the clock, so this is the moving observer's period of his clock or her clock, delta t prime, longer than the period or the proper time, delta t, in the frame of the clock itself? And I'm going to show examples of the clock at rest. This is from Wikipedia also. And the clock at rest with the moving observer from Wikipedia. So then I'm going to show another example that will express special relativity and show that where I believe you can see where I'm coming from, that it's a two-signal time delay theory. And then with this as a background, I'm going to show you the alternate viewpoint, and I believe the correct formulation for the phenomena of what we call, what is called in special relativity time dilation. But I think the correct way to look at it, it's really a transverse relative time shift per Henry Dowdy or Edward Dowdy. So time dilation, the simple inference per Wikipedia. I have the link at the bottom here. So if you just do time dilation wiki, you'll probably find the paper, you'll find the reference. So time dilation can be inferred from the observed constancy of the speed of light in all reference frames dictated by the second postulate of special relativity. This comes directly from Wikipedia. This constancy of the speed of light means that counter to intuition, the speeds of material objects and light are not additive. It is not possible to make the speed of light appear greater by moving towards or away from the light source. Now, again, I'm going to emphasize this is a quote from Wikipedia, which is just, I just want to make it clear that this is not what Henry said, Dr. Dowdy. So here's a diagram, and the diagram on the left, you have a light clock. So you'll have a mirror A at the bottom, a mirror B at the top. And what you will have is you'll have a light source ping, like say a pulse, and the pulse will go up from mirror A to mirror B, and then bounce back down to mirror A. And it 2 times, okay, so if you take the length, which is the length between the distance between the mirrors, and you divide it by the speed of light, and you multiply it times 2, you'll get 1 tick or 1 time reference for the change in time. So it goes up and then down, and then up and then down. And now what supposedly on the right is the way it is viewed when you have the mirror A and B fixed in space, but you have an observer on the right moving towards the left. So it appears that the mirror itself, the mirror light clock on the moving observer, it appears to that observer that the clock itself is moving to that person's right. And then you get, we'll go through the formulation of the triangle here. So that's what this delta T prime is here. It's what the moving observer appears to see what the light clock is doing from the observer that's moving from right to the left frame of reference. So then, excuse me. I'm on TV. We're good. Sorry about that. Did a little distraction. It's my bad. Okay, so the left clock, the observer at rest measures proper time, 2L divided by C, between the co-local events of light signal generated at A and arriving back at A. So delta T in this time is 2L over C. So on the right clock, you'll have events according to the observer moving from the left in the setup. Bottom mirror A, when signal is generated at time T naught, that would be right here. Top mirror B, when the signal gets reflected at time tau prime, right here. Top mirror B. And then it says at time D divided by C. And then, of course, you got to multiply it by 2 to get it over here back to mirror A. So the observer is moving with a velocity V from the right to the left. And let's see. So the observer moves to the left. This is time dilation. You'll have, if you take, let me go back up here. Sorry, I'm going back up to the previous slide. So you have really a right triangle, D as the hypotenuse, and then you could call this horizontal direction 1/2 V delta tau prime. And then this vertical, the distance between the mirrors is L. And so you have, per Pythagoras, you have D squared is equal to this bottom length squared plus the distance between the mirrors squared. So basically, also just solving the equations, and you wind up, voila. If you start doing your substitutions, you'll wind up with the per wicket, this expression, which expresses the fact that the moving observer's period of the clock, delta tau prime, is longer than the period delta t in the frame of the clock itself. And so I just want to take a look at this. So if the velocity is increased, you'll have 1 minus a number that's approaching 1. And so then this number gets smaller, which this number gets bigger, and hence you get your time dilation. Now, remember, this is per Wikipedia, but I think it pretty well mimics what I've seen in relativity literature, other relativity literature. So I'm holding this here for just a second so that y'all can kind of absorb it. Now, this is what they're saying. So I pose a question: is the moving observer's period of the clock, delta tau prime, I'm just going to call it from now on, longer than the period tau in the frame of the clock itself? So let's just take a look at this. This is what they say that's happening. They say that if you're an observer over here with the velocity moving from right to left, you'll see the mirrors move from your left to right. And then the path of light would actually go from the A mirror to the B mirror to the A mirror in this triangle configuration. So what I did was I set up an experiment. This is this is just an artist rendering of what I think is really happening. So I have the top right corner. What we're doing is we have this is in top left corner. I'm sorry. Time t equals 0. I have the observer on this horizontal line right here. It's 1, 2, 3, 4 units of distance to the right of the clock. And so this is mirror A at the bottom and mirror B at the top. And it's on the y-axis. The observer is on the x-axis. And I have a ball representing a light pulse. So at time t equals 0, which may be a little difficult for you to see, but this is time t equals 0. The pulse begins at the mirror at the bottom, A. And at time t equals 1, the observer has moved 1 increment of distance, and the light pulse has gone 2 increments of distance. So at the speed of light. So it's a very fast moving observer. But anyway, that's kind of a bad joke. But anyway, what I'm doing is showing that as the observer moves at time t equals 2 or t2, it's moved 1 more increment of distance while the light pulse has moved 2 again. So it went from 0, 1, 2, then you'll have hence 3, 4. So here's 3, 4 in 4 distant increments of time distance. You have the light clock has gone, the light pulse has gone from the bottom mirror A to the top mirror B, and the observer has gone 4 units of distance. Actually, the light pulse has actually gone in 4 units of distance from the observer's perspective, 8 units of distance in the mirrors, in the light pulse's perspective, but you can see what's happening here. So then, let's see, so at time t, 3, 4, okay, so now at time t equals 5, the observer is past mirror A, because it's fixed, remember, and the observer is the one doing the movement from the left, from the right side of the frame to the left. And now the light pulse is headed down towards from mirror B back to mirror A. And up at the top right block at time t equals 6, the observer is right here, and the light pulse is here, and then T7 and T8. So now at from time T0 to T8, the light pulse has gone back to the clock. The clock is fixed in the reference. It's the fixed reference frame. And then you have the observer is now at position here at T8. So the light clock is a fixed in space observer while the observer travels with velocity v to the left, denoted by the position x, the position of the observer. So the light clock is fixed in space while the observer travels with velocity v to the left. So the velocity of the light is fixed. It equals c. The velocity of the observer equals v. The observer moves with a distance 1/2 v tau prime. That would be the distance here, or the distance between T0 and T4, or T4 and T8. The observer moves that distance as the light pulse moves the distance one way to the mirror and then back. That'd be the full distance. So the light travels path L from the bottom mirror to the top mirror from time T0 to T4. Light does not travel path D. If you'll notice, the light is not moving from this path D here. The light is just bouncing back and forth between the mirrors. The moving observer thinks that the path D is the calculated path of the light. So he thinks, or she, there is a delay of that tau prime is longer, that the delay tau prime is longer than tau. Wait, something is odd in the diagram to the right. Okay. So basically, I did not go through any kind of, how would you say, artist rendering of what I think if this light was a spherical source, constantly emitting out spherical light, what the observer would actually see at any given time. That's for a different discussion. I'm just trying to make the observation that in a stationary clock, something's odd because what a person thinks may not be actually what is reality. So wait a minute, something's weird. So D equals delta 1/2 tau prime C. Is that correct? I mean, because light's not really going from along this hypotenuse. It's going up and down. So let's just follow this argument so I don't mess it up. Let's see. Observer, let's see. So light travels the path L from the bottom mirror to the top mirror from time T0 to T4. So from here to here is actually tau, not tau prime. So this is tau, and we know that already. That was in Wiki also. Observer with velocity v moves distance x tau naught to x, position x, tau t4, time t4, which would be from here to here. So that's the critical thinking that I've come up with anyway, if it's that critical or not. What we have is the time that the light travels from the bottom mirror to the top mirror is 1/2 delta t. It's not t prime. While the observer moves the distance in the horizontal direction, which is not delta t prime, it's actually delta t. So this distance from x equals t0 to where x is at time 4, should be delta t, not delta t prime, because when the observer that's moving from the right to the left goes from t0 to t4, the light clock has gone from the position at the bottom mirror to the top mirror. So these two times are the same. Okay, so the horizontal time and the vertical time are the same on the first half of the first triangle. So delta t prime has no meaning for the defining D in top figure. That's why I put the question mark right here. What is this time? There's nothing actually going from here to there. Okay, so then tau equals the time from T0 to T4. So it's the same for the fixed clock and the moving observer. And so the moving observer is going this way while the fixed clock's time's moving, the light clock is going from here to here. So if you take and you solve the equations, you'll find out that this is what you really get. You really get D, this distance here, is just 1/2 tau times the expression in the square root of c squared plus v squared. It's not equal to 1/2 tau prime times c. So the correct expression is at the bottom, I believe. So is the moving observer's period of the clock tau prime longer than the period of tau, the proper time, in the frame of the clock itself? So I go, where is tau prime? It's kind of disappeared. When the observer travels with velocity v, the observer's clock rate is tau. See diagram. So if you have an observer moving at velocity v from point tau, t equals 0 to t equals 4, the light clock has moved up here, that distance, and it says observer's rate So when the observer travels with velocity v, the observer's clock rate is tau, not tau prime. In special relativity, the moving observer's clock rate is defined as tau prime. The fixed clock per proper time, that would be tau, is the same as the moving observer's clock rate. So tau prime equals tau. The conclusion is the proper time for the fixed clock and the moving clock are the same. Now, I don't know why I put time dilation per wiki. Basically, this is my expression. It's not really from wiki. So I want to validate this by just saying, okay, we're going to look at this, and I'm going to do a trick that the relativistics, and that's done in relativity that makes a lot of sense. You just got to remember what c means. Is it a distance or is it a velocity? So what I'm doing here is I'm just saying let L, this distance between the clock, equal 4c in meters. So here c is basically going to be a distance. It's just the distance in 4, it's 4 times c in distance. So we know light travels 3 times 10 to the 8th meters per second. So that would be the distance. So 4 of those distances. So that's why I have the observer being very small and the mirror, the light clock being very large. That's a joke. But I guess this could be cut and dimensionally put down into smaller sizes, but then the time increments would be a lot smaller. So basically I have 4c distance here. Let's see. 1, 2, 3, 4. And I have 3c distance along, you have 8 distances between the mirrors, and then you have 4 increments of distance, but that the observer moves. And so that would be, if you just start following the equations, you have L is equal to 4c. So this L would equal 4c is 1/2 delta Tc. So that means if you solve the equation, you get 8 is tau is 8 seconds. So in 4 seconds, the traveler goes from here to here, while the light pulse goes from here to here. So wait a second. I think I made a mistake here. This should really, it's really 4 seconds from here to here and 4 seconds from here to here. So let 1/2 this equal 3. The velocity is 3/4 the speed of light, so I'll need to fix that. Let's see, did I propagate that? Okay, sorry about this. Let's see. So if we're letting the velocity in the equation where you have 1/2 delta TV equals 3c, because this is 3c. You get 3/4 of the speed of light. Okay. So really what happens is you have the light pulse going this distance between the mirrors. It's traveling the distance 8c, where the velocity, the person is 4c, where this person has gone this distance. So it's gone 3/4 c is the velocity of the horizontal observer. So d is equal to 1/2 delta t c squared v squared the square root of. And if you solve the equation, you get d is equal to 5. So this distance is 5, this is 4c, and this is 3c. Which is the hypotenuse. It validates. You just have 3 squared plus 4 squared gives you 5 squared. So is the moving observer's period of the clock tau prime longer than the period of tau in the frame of the clock itself? Time dilation equations do not apply. The clock is fixed. The clock rate is not changed. And tau prime, no, since tau prime equals tau. Okay, so in special relativity, I'm going to give you another example. You have in special relativity a two-signal time delay theory, the right triangle. So here we go back to our friend 3c, 4c, and 5c. And with the velocity of the speed of light, approximately 3 times 10 to the 8 meters per second. And what I have is some positions here, P, Q, and M. So the distance 5c is equal to 15 times 10 to the 8. Time T is in seconds. And the observer, I put a happy face up here because that's where the observer is. So in this example, basically what we're having, you'll see what's happening. The observer is located in position M. So actually the face is here, but the position M is right here where the red dot is. So let the fixed source emit signal P, S sub P. So let the fixed source S at position P emit signal S, little s sub P with velocity C at time T equals 0. So really what we do is we have the position of a source at position P at time T equals 0 is going to, that's where the T equals 0 is right here, is going to emit a spherical wave or a signal that is going to head towards the direction of the observer at position M. And so I'm going to graphically show this by pictorially show this, that so at time T equals 0, a spherical wave is emitted at position P, which is fixed in space. And at time T equals 1 second, the wave is reached this distance. In 2 seconds, this distance, it's gone 2 distances of C. And now at time T equals 3, time T equals 4, and then finally at time T equals 5, the observer receives the signal. So another way to show all these graphs in one graphic is to go ahead and say, okay, you have a source emit a signal, a fixed source emit a signal at position P. And in 1 second, the signal has traveled this distance. In 2 seconds, this distance, 3, 4, and hence 5. The observer receives the signal at here in space at position M in 5 seconds. And you have this distance is 3c of a distance, 1, 2, 3. And then this distance up here, if you were to move it over, you would see that this is 1, 2, 3, 4 distance right here. It's a parallelogram right there. Okay. So this right-hand figure is just a shorthand way of showing the phenomena if you just follow the time increments 0, 1, 2, 3, 4, 5 seconds. Now this is going to be helpful because we can combine these and you'll see in a few minutes what's happening. So let the fixed source at position Q emit signal S sub Q with velocity C at time T equals 5 seconds. So with this shorthand way again, I'm not showing all the other circles in blue, that I'm just showing the 5 second one. So P did the second, initiated a signal at time T equals 0. At time T equals 5, the observer sees or receives the signal at position M. Another source at position Q sends out another signal at time T equals 5 seconds. So I'm ignoring the first signal right now and just focusing on SQ signal. So in one more second, which would actually be T equals 6 seconds, the signal has reached this position. In 2 seconds, the signal 2 at time T equals 7 seconds, reaches this position. This would be 8, and then obviously 9 right there. So in 8 seconds and then 9 seconds, the observer has now received signal S sub Q from source Q, which is fixed in space. I'm going to go back here. So then what we can notice is that the delta T from Q to M in distance is 4 seconds. And so SQ travels 4C in 4 seconds from T equals 5 seconds to T equals 9 seconds. Okay, so remember the original signal started here, not the original signal, the signal from source P started at T equals 0, 1, 2, 3, 4, 5. At this time, source SQ, the source at position Q, emits a signal. So at 5, 6, 7, 8, 9. So this is 4-second time delay. This is a 1, 2, 3, 4, 5-second time delay. So the signal SP and SQ flight paths from fixed sources. So now we have this figure on the right, which basically just says what I just showed you. So if you have a source at Q and it emits a signal at time T equals 0, in 5 seconds, the observer reaches that signal. If you take that time delay, which is the same as this horizontal distance, it's really just a horizontal distance. It's a time delay from this position P to the position Q. At 5 seconds, you initiate a pulse at position Q. 4 seconds later, the observer receives that signal. So we call this the distance between, in the previous examples, this distance would actually be the distance between the mirrors, for example, between P and M. And that would be our delta time or proper time right here. Remember, all this is fixed in space. There is nothing actually moving from position P to position Q. We just have a time delay, which can be done with circuitry and stuff. And so another thing too, that this is introducing some of the work that we're going to read here about from Edward Dowdy. He would refer to the birth signal and the death signal. So, well, it's a birth signal. The birth signal is here. It reaches M. And I'll just leave it at that. Let's see it. Then this signal is birthed here, but we'll talk more about that. And it reaches M here. So the time delay is 5 seconds to reach the first signal, and then that second signal is emitted at that time, and it's 4 more seconds later at time T equals 9 when the observer gets the second signal. So tau prime, let me go back here. Tau prime is actually 5 seconds, and delta and tau is equal to 4 seconds. So this is the same formula that we derived earlier. Signal SP and SQ flight from fixed sources. So the source is fixed. Now, in the previous example that we had with mirrors and the observer moving from the right to the left, I'd already had this one set up where basically you have an observer moving from the left to the right. If you want to look at it, there's nobody moving in this example. It's just these are fixed sources. But that's the illusion that special relativity is trying to give you. And I'm just trying to say that this is not an illusion. This is fixed sources. And you have at position P and Q, and M receiving the signal with these time delays called tau prime here along the hypotenuse. And this time the light is actually moving. The light is actually moving from these fixed sources, where in the previous wiki example, there was no light going from the observer to any mirrors. It was bouncing between the mirrors. And then the proper time, but it would be a Q put from position Q to position m right here. And here's your formula that I derived earlier, which is not, it doesn't look like the one in Wikipedia. Okay, let's go to the next slide. So now here's another example, and we'll go a little quicker here. So the rocket traveling with velocity v, let's just try now a rocket, and we're going to have it go from velocity v passing point P at time t equals 0. Okay, so the fixed location M, P, and Q, and the rocket's position is at P at time t equals 0, and its velocity is going from, it's moving from the left to the right. So then what we have is the rocket position at time t equals 0 is here. At time delta time across from here, it's at, when it's moved this distance here, we're going to call that tau prime. And its position now is at Q. And so let's just let tau prime equal to 5 seconds. Some of y'all might know where I'm going with all this. But let's just say that the time it takes for the rocket to go 3c distances is 5 seconds. So the velocity and the distance, so the velocity of the rocket is 3/5 c in meters per second. Okay, now I have a slide here that says caution, avoid temptation. And I've kind of thrown all of this into one graphic. And basically what I'm saying is you'll have this figure to the top left corner where you'd have light signals from fixed sources reaching the position M with these time delays. Tau prime is the time delay of the signals between the two signals that were emitted, and 5 seconds, it was the time, which is equal, tau prime is equal to 5 seconds for the first signal to get to position M. And then the second signal 4 seconds later is tau between these two fixed sources, which could mimic the mirrors in the light clock. And then you wind up, I drove the expression for that. But remember, there's nothing moving between point P and point Q, like say a rocket or a moving source. These are fixed sources. So then I have the rocket example in the bottom, where you have a rocket that just happens to coincide with the same tau prime in the previous example. So that it takes 5 seconds for it to go from position P to position Q, down here, P to Q. However, it's not a light source. It's just a rocket. It could have done this on a different day. It could have done it the day before. It doesn't matter. It's just an example of a rocket or something. It could be a muon or whatever going from position P to position Q with a certain time delay that happens to be the same as the example above. So now if you add them both together or you superimpose the diagram, remember the light sources are fixed in space. And so this rocket ship now is just passing this position at the time that the light is emitted from the source at P, and the time the light is emitted at source at Q. And then you wind up with the formulas that the time dilation formula. So but here's what I wanted to, let me go ahead and follow my example. So the rocket position P, T, 0, it's at position P at time t equals 0, and at position Q at time tau prime. So let that equal 5 seconds. It's traveled 3c, this distance m at the horizontal distance. It's traveled that distance in tau prime. The signal positions are P here and Q here. And of course, you have the time delay between the two signals. So the velocity v in m is equal to v delta tau prime, is unique to the rocket velocity and independent of the signal velocity c. The signal delay tau prime is synchronized with the rocket position with velocity v. There's no cause and effect between the rocket position or the speed or signal emission. The rocket does not emit the signal. The source is at P and Q, and they're fixed. So caution, avoid temptation. So what I've done is I've taken the previous diagram, you've seen this before, and I say, let's take for the signal SP and SQ, let's take these signals here, and let's take and square these distances, and you wind up with this formula. Then what we want to do is we want to say, oops, let's take M, and now here's for the rocket. So for the rocket, you have M is equal to V tau prime, and that'd be the velocity times its time would give you the distance M. Let's just plug this variable in here. And then you wind up with this expression here, which looks familiar. It looks like it comes from the wiki. And what you do, let's go to the next slide. You plug it in and voila, you get the time dilation formula. But I'm going, whoops, something's not right, because this is bad physics. You can't take this expression from this figure over here to the right, which is a moving rocket, just happened to go from position P to Q in what you would call, in tau prime, and then plug that into this expression here and wind up with this expression over here. And that's not right. So anyway, I just show that this is kind of like showing a contradiction in physics. So I perceived or whatever that in special relativity, tau, this trick with tau prime and tau of a moving observer and a fixed clock has kind of introduced something strange. And I've noticed that, because they say the constancy of the speed of light, when something is moving through space, it emits a signal. I just noticed that the signal is being emitted from something that's not even moving. It's a fixed position in space. So now I'd like to go ahead and introduce an alternate view. And we will derive a formula for extinction shift theory. And I think we can appreciate this. So this is an introduction to extinction shift principle, a pure classical replacement for relativity on the Transverse Relative Time Shift by Edward Henry Dowdy Jr. And what I've done is taken one section of this paper, and you can get this paper from this link below. Yeah, I can't really give it to you right now, but maybe I can give it to you while we're having discussions later. So the light sphere, or a light sphere or circle, travels outward from, these are some premises that we have to understand first, with velocity c. The radius of the light sphere is c times t. So as the sphere is expanding, you have the speed of the light times time will give you the distance. And the source moves with constant velocity v. So we're not talking about acceleration here. So the center of expanding light sphere is the source. So as the light sphere expands, the source is in the center. So, and if you'll see where this is important here in just a second. So observers perpendicular to the death signal. So basically you'll see what I'm talking about there. The birth of the signal is the initial signal. The death of the signal is when the signal is extinguished. But we'll go to that. Let's see. But it's actually a separate signal that the observer will see, and we call it the death signal. So in extinction shift theory, I'll explain this diagram here, and then it'll start making sense as I start going forward. The light sphere circle travels outward with velocity c. So at time t equals 0, I have the source right here. And so this would be, you would say, the y-axis, and this could be the x-axis. And of course, all this is in 3 dimensions. You're just seeing it in 2 dimensions. So it could be a sphere. I'm only showing circles here because we're in one plane. So the radius of the light sphere is c times t. So at time t equals 0, we have something over here to the left going to the right, and it emits a signal. And the signal source is moving at velocity v from the left to the right. And then everything else is fixed in space. It's a fixed frame. So in this example, V is less than C. And at time t equals 0, the signal is right here, and this blue arrow represents the velocity vector. And since it's just a dot, it's just at time t equals 0, the source is emitting a signal. Okay, so the light sphere, this is what the light sphere looks like at time t equals 1 second. It has expanded with a radius of 1c, and the whole sphere has been expanding and moving from the left to the right. So I'm doing this from my left to my right. It's gone like this because the center of the circle maintains, and this is in free space outside the light source and any other, masses or reflection points or whatever you want to call them, secondary sources. So as the light sphere is expanding, it's also moving to the right, with the center being maintained at the source. In 2 seconds, the light source is right here, and the circle, if you'll notice, is at the center, or the sphere is at the center of the sphere is still maintained where the source is. So the source is moved from, in time t equals 0 seconds, from the origin to 1 second to 2 seconds. And you can see how the circle is expanding here away from the observer. And the way I look at this is, if I was on a rocket ship and I was shooting fireworks, if I was on like a battleship going through space and I was shooting fireworks up in space, I would look up in the sky and it would look to me like they were going, the fireworks were still above me, even though I was moving with the velocity of this. As long as there was no electromagnetic interference or some kind of radiation or whatever out there, if you were in empty space, this makes sense. So in 3 seconds, the light sphere has gone 1, 2, 3. Here's where the source is. And the sphere from the original pulse is right here on the outer edge, and meets an observer at the t equals 3 second point. Now you'll notice this is visually, you can visually appreciate this viewpoint. The reason why is you can see that it's 3 seconds ago the signal was emitted, and the light actually traveled this distance to make it to the observer, while the source has actually traveled a shorter distance here. And so instead of calling, in relativity, now I'm just going to introduce this for a second, because of a comparison, because it's easy to see here. Instead of this being called tau prime, and this distance here being called tau, look at it this way. The signal was birthed at time t equals 0 seconds and reaches the observer. So you have tau naught times c. But you'll also have to include the velocity of the speed of light in that, in your thinking right here. It's v plus c to get from this point to this point. So the observer receives the first signal blue in time tau naught. The second signal red is emitted by the source at time tau naught. So when this observer receives the first signal, the traveling source, which is moving at velocity v, emits a second signal, and we're going to call that the death signal. So the burst signal is when the first signal is emitted. The death signal is the second signal. So, and now what is this cone here? I call the birth signal light cone. Now, this is important. It's not, technically, it's not what special relativity would call the light cone, because the light cone would be anything that shows up inside of any of these circles. But this is just a reference. I'm taking the 90-degree position and calling it the light cone. This is something that this is not what Henry Dowdy said. This is basically what I've said, just to make that clear here. And so at the time, the second signal, we call it the death signal, is emitted. The observer receives the first signal. Now, obviously, it can't see the second signal yet. So henceforth, we have at 4 seconds now. You see the second signal being emitted right here, and it's evolved to this shape right here. Of course, it's spherical, and we're only looking at it in 2 dimensions. In 4 seconds, in time t equals 5 seconds from the initiation of the first signal, but we have the signal evolution to this distance. However, you'll notice it's only 2 seconds old, the red signal. So there's 3, 4, 5, 6. So in 6 seconds, the observer reaches and observes the second signal, which is really cool, because it took 3 seconds for the second signal to be even birthed, or we call it the death signal, but for it to actually happen. And so you have this 3-second time delay for the observer to get the first signal, another subsequent 6-second time delay for it to get the second signal. So at time t equals 9 seconds, the observer gets the second signal. So now we can use our, so we have tau and we have tau prime. And you'll see the observer receives a second signal red in the absolute time, tau naught plus tau prime. Now, remember, so yeah, we can look at this diagram for a minute, because it takes a little bit to absorb. So in tau naught, it receives the first signal. In tau prime, the observer receives the second signal. It's tau naught plus tau prime when the observer receives the second signal. There you go. And that's called a transverse relative shift, not a special relativity time dilation. And if you take this squared is equal to this distance, tau naught v squared, and then I'm sorry, this is tau naught c is from here to here. That's something I kind of glossed over, but I should have showed that to you, and it's kind of hard to see. But if you see these little arrows from 1 second, it's gone in the downward direction. The light has traveled 1 second, 2 second, 3 second. So that's tau naught c. So in the up and down direction, there is no velocity component to add to the light signal in that direction. So it remains unchanged. Okay, that's important. And so you can square that, square this, and you will get this distance here, the total distance from the origin to where the observer is. And then the same thing here. So in tau prime v, you have 1, 2, 3, 4, 5, 6 seconds times the velocity is this distance. And then you have tau naught c is how long it takes the light to go from this position to that position. If you square those, you'll get tau prime c. And if you solve for tau, so let's just look over on this side. If you take tau naught squared plus tau prime v squared equals tau prime c squared, and you solve for tau prime, you get the formula from that special relativity calls time dilation. So basically, I think if you're looking at special relativity from the perspective of Henry Dowdy, you would call it a transverse relative time shift. It's not a time dilation per se, because you'll notice one thing in all this: the clock is all the clocks are synchronized. And that's about as much of relativity as I can say. So I go, the light sphere or circle travels outward with velocity c. The radius of the light sphere is c times t. The center of the expanding light sphere is the source with velocity v. So as the light source is moving across with velocity, the light is expanding with the source at the center, and you get a v plus c at the wavefront of the expanding sphere. The observer is perpendicular to the death signal. And that's a key thing. To come up with this infinity or this formulation where you have the infinity here that as you approach the speed of light with the observer at a perpendicular position, you will get this infinity. You'll get something, some equation that will have infinity in it. And there's a reason why. And that's something that we should think about. Let me see what the next slide is. Okay, so I'll talk about that a little bit later if you're interested. But well, just look at it for a second, because this is important. And I'm going a little bit over my time, but that's okay. If you're the observer here.
Sorry, it's not by any means restricted to 1 hour. Just to say that you're not really going over your time.
Okay.
It's up to yourself.
I'm almost done anyway.
Okay.
Okay, thank you. But there is something that I observed, and I know I can't defend this. I can just say this, that when I would talk to Henry Dowdy and got all excited about his work, which I'm hoping somebody can get excited about this. I'm probably not doing that good of a job. But I said, there's a reason why we have that infinity. He said, speak on, I said, look, we have this thing that in relativity, in special relativity, they call a light cone. And, they talk about the future, the past, and the present, or observability, or whatever. I'm going, if the observer was inside this second light cone, see, you've got the blue light cone and the red light cone. Since we're going below the speed of light in this example, that's why you see the bunching of the waves in the aft end, and in the fore end, you see them spreading and advancing. I said, move the observer inside the second light cone so that you will always have observability. And he goes, I think he used, I can't remember, but he said, that's brilliant. That's all I heard him say. And that's all I can say, I'm nothing. He's the one that did all this. He got to this point. And that's all I can say. So, and that's what kind of got me excited, was he gave me a little spark of interest to proceed, because I just saw this. Now, I know there's going to be people that aren't going to get here yet, but that's okay. The key is you can help remove the infinity by moving the observer inside the secondary light cone. But you got to be careful, and that's where I've made a mistake, and I have to go back through this big lengthy paper that took me 2 years to write, and I have to correct it. It's a simple correction mentally. It's a difficult one mathematically. But so the point is this: you realize that what really people are looking at is, what is this ratio of the time differences and the solution to it? And you can solve a lot of things. So if you just take this ratio, tau naught under tau prime, and then you wind up with this ratio over here, you can remove this infinity by putting the observer inside the light cone so that it's always getting two signals. Now, this has a lot of implications in frequency theory. The Nyquist principle, for example. Why does that even exist? Well, it's a well-known thing, and I'm not a radar person, but I just know when I took a class in college, they said there's a Nyquist principle. You have to always subdivide your frequency time, your time slices in this physically based algorithm where you're trying to filter out noise, or you're trying to solve nonlinear differential equations, you have to have a time slice that's at least 2 samples per every, you have to have a time slice smaller, so that, and that comes from here. If your time slice is too small, you're not going to get all the information. But in this example, if the birth and the death signal or your time slice is small enough, and the observer is inside both light cones, then what happens is you can get observability, and that's what you want. And I think that's what happens in nature. That things fly by us all the time, and nobody ever cares or knows because we don't observe it. But I think it's just because their velocities are so extreme that they don't interact. And when they rarely do interact, you get this big, thing that happens in one of these bubble chambers. Okay, so enough of that. So conclusion, Edward Dowdy's extinction shift principle for transverse relative time shift is explained. In transverse relative time shift, the single source moves with constant velocity, and the light signal center coincides with the source. And we're talking here about primary sources. We're not talking about reflections off of like the observer, etc. The infinity in transverse relative time shift can be removed if the fixed observer is inside the second light cone. Why? Because the first and the second signals can be observed. The constancy of the speed of light in special relativity implies that the light sources are fixed in space and not moving with velocity v. That's implied, I think. What they'll do, you notice one thing I have not mentioned at all is frequency. The way they get around it in special relativity is they'll say, oh, the frequency has changed. When the moving source emits the light, even though it's going, it's, the source is over here and the light's going like this. And I'm going, that doesn't, they'll say, oh, you get a Doppler phase shift. You get a phase shift, or you get some kind of frequency shift. And that's how they come up with their, energy. And they'll say with energy, you get more energy. It's moving at a velocity, blah, 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 blah. And I'm going, something's not right here, because it's a fixed light source. You don't even need the source from their perspective. It's the constancy of the speed of light in special relativity implies that the light sources are fixed in space and not moving with velocity v. In special relativity solution for time dilation is a time delay theory. The moving objects are not light sources. I mean, if you were to make them light sources, then you would get different, you would actually get physics, I think. So, and you would get measurements. And so anyway, I think that might be it. Okay. I think what do I do now, Ian?
Well, Harvey,
Stop sharing.
I think it's up to me to take your slides down if you wish to do that.
Yes, go ahead. And okay. You can, and if someone wants to show a slide, you have them, or you can make me the presenter. How do I do? We can figure that out.
Yeah, we can. Well, unfortunately, the only people who can present slides are those in the green room. If any of the general participants want to, they'll have to give us a link or something,
Okay, I can start taking questions now, and I'm sorry I wasn't able to stop, and I can't. Okay, I'm ready to go forward now.
Well, you did stop sort of 9 minutes after the hour, which is fine. I mean, it's not actually restricted. I think we thought that it was ideal if we had a 50-50 split between questions, but you have a little more, so that's great.
Okay, so go ahead. Yeah, questions, right. Whatever.
Right. Well, I might just spend a moment going through some of the questions coming in. I think there were not very specific questions, more of a discussion. But just for my own part, I was interested to see that the Galilean composition of velocities comes into this system. And I was wondering if this is a reciprocal effect, with regard to the source velocity vis-a-vis the observer velocity, because in the Well, I suppose if you're looking at any wave disturbance, such as sound in air, you find there isn't reciprocity. You find that if the observer is moving towards the source, well, of course, there is an addition of speeds, and contrary-wise, if he's moving away, it is subtraction from that. But that isn't the case if the source is moving. In the medium, let's say in air, in the case of air, and that's basically the second postulate of SRT, that the speed of light is independent of the speed of the source. So that's contrary to what Ritz said, but it seems to comply with all other views. And yet, I think from looking at it generally, maybe with the extinction shift, am I right? It says that actually there is an addition or subtraction of velocities when the source is moving.
Yes, sir. If you look at his paper, I could bring it up if you want me to find it and bring it up. I really should take that link and put it in the chat maybe for people. Right?
Yeah, you might do that. You did, I think, give this to us earlier on, and I had a look at it myself. It's
okay.
Pretty
so
complicated maybe to look at in a short period, but I think people might be interested in looking at it later.
Yeah, what Henry Dowdy does is he starts adding. He had, this is only one section of his paper, and he goes through many phenomena, and he actually shows how frequency changes and wavelength changes as you do the velocity of a velocity of a moving source. And so when something receives that, I get the impression it re-emits it. But it re-emits it. He calls them moving windows. Like if one source is moving, I can't see now. Okay, here we go. If one source is moving this way, and the receiver is moving this way, this receiver now can become a secondary source, and its velocity is added to the previous one. So you got it's not. Well, I said that wrong. It receives it at a signal, and then it re-emits it at C from its frame of reference. It's a new frame of reference. That's the way I think. So what happens is you follow all the different sources and the secondary sources and there's always the original primary source. So what we see in space, for example, they say, well, the binary star algorithm doesn't work in a Galilean transformation world, right? Well, the thing is it's surrounded by a cloud, a dense cloud of plasma. And so as the signal's going through, as the stars are emitting light and moving away and towards you, yeah, the frequency's changing and up and down and all that other stuff, but it's absorbed in the cloud and re-emitted. And so it's a very difficult problem to say, you can't say Henry Dowdy's theory is not right, because it's got other sources that are fixed, re-emitting it at sea. But I think it's wonderful that we can look out in the heavens from vast distances, and we can tell things are relatively still changing in motion. You know what I mean? They're doing that. They can tell that spiral arms of galaxies are moving away in one part of the system and moving towards us in another part of the system. And they can actually come up with calculations. So okay, I'm sorry. I'm going.
It certainly seems to be quite a powerful predictive tool. I mean, he comes up with the equations of GRT, things like mercurial precession and so on. But personally, I will say, I'm going to hand it over now to the questions, but personally, I'm not convinced. I think it's a model which actually seems to have some merit. It seems to work, but I'm not convinced that it's physically correct. So you might have a word to say that at the moment. But I have a question here, even about the light clock itself. He says, I can't find the source for vertical light clock. Was it really Einstein or someone else?
Yeah. It's Wikipedia. What I'm going to do is.
Yeah, they do talk about it, but I suppose it did. It's a development of the earlier ideas from a lot of papers.
What I'm going to do is here. I'm going to. Go ahead and talk. I'm going to go ahead and
okay.
Control C.
Yeah, if you get any more information on that, we can put it up. But
There's the
this
link.
person, JG, has been talking a bit about this, and I think Ned also. I think on one occasion, I can't actually find the comment here, but I think they said we thought you were going to be more in contradiction of relativity. You seem to be supporting it in some ways. I think that was one of the comments, if I got it right. But
Okay.
here, maybe this is the one I'm looking at. I don't know. I thought we were trying to refute, not support it. Well, I dare say, if I may speak for you as well, we're not trying to confirm or refute anything. We're just looking at the evidence and seeing where the most logical conclusion is.
Okay, Ian, I put the link to Dr. Dowdy's paper in the private chat, and also I put the Wikipedia link for time dilation in the private chat also.
So what I might do is I might copy those and put it into the public chat as well.
That'd be cool. So no, really, I think special relativity is wrong because they say the sources are moving and emitting, like a signal. And I'm going, not in special relativity. They're fixed sources because of the constancy of the speed of light. And that's what I tried to show. Now, Henry Dowdy shows a physical reason why you can derive the extinction shift principle, which looks like the special relativity time dilation equation, right. But it's only in a restricted sense. It comes up. In other words, that somebody can derive a single, a math equation with their explanation on a chalkboard or whatever, but it may not have anything to do with the reality of how that physics works. So Henry showed, I think, the correct view, the correct way of deriving that formula. And it has to be with V plus C, and it's Galilean transformations in, I forgot the other term. I'm not the expert in this space, Newtonian mechanics or whatever. It's, I forgot.
Right. Well, in the green room now, actually, Jim Keane has been posting a few things, and I was tempted maybe on one or two occasions to suggest something, but I didn't feel confident enough, so I thought we might leave it.
I see death signal. I see that. Okay, James. Yeah.
So maybe if I could bring James up, with your permission, James.
That's cool.
It's good to see you, and maybe let you post. You made a few points, and maybe make them directly to Harvey with the reception.
Yeah,
well,
ahead,
I guess I don't think I understood enough of what was being presented to probably make even intelligent questions. It's raining pretty hard here, so maybe let's go to another. It's sounding on the roof, very loud.
Okay. Well, the death signal is basically just another signal that he calls the death signal, so that you can get the time increment. To calculate a distance to start with. That's what it's just your second signal. And I've heard before from other people that they don't like the idea of death signal, but it gives you a reference frame of the start and the stop time for the experiment. Like what is your distance, your original distance or time increment that you're talking about. So you start it and you have a second pulse, or you can have a third, a fourth, a fifth pulse or whatever, and then you just track all these things. So in special relativity, I guess it would be the time from the bottom mirror to the top mirror. That's your clock proper time. But the time it takes the observer or the source, something to move across, like with the velocity, that's a different incremental time. Okay. Okay, I'll be with you.
So, in a way, maybe the conventional view is to say, well, look, as you pointed out, Jim, yourself, it's going a longer distance in the same time, so time must change and so on. Whereas if we bring in the composition of the speeds as an alternative explanation, well, that seems to comply more with this idea, and indeed with common sense. You don't seem to get all these paradoxes, in other words.
Mm-hmm. And it also implies that there's a single reference frame for time. In other words, nothing's affecting any clocks. And so that's where I'm thinking now. But I can't really, I don't want to bring that in here, like what's the next, what's next? I mean, I'm only gone to a certain beginning understanding of, thank you, a beginning understanding of what Henry was communicating, and I've been looking at relativity for 40 years, but it's like you can just memorize all this stuff and memorize these equations, but what's really happening? And I don't think, see, I haven't mentioned gravity, so I haven't seen or dealt into what Henry is saying about gravity either. I mean, that's something where I've got to do some thinking about.
Do you know, by the way, if he came to his ideas, and in particular, whether in opposition to the main views, by degrees, or did it occur late, or was he always skeptical? You don't know, because you didn't have that. You didn't really meet him, did you?
No. I've had a couple of webinars with him, and that was it. No. Phone calls, and then I've looked at his site, which has been brought down.
It's been brought down, has it?
Yeah, I can't find it, and if somebody finds it back up again, let me know. But I was in contact with his daughter, and someone else, I don't remember the name right now, had taken a lot of snippets of his information and put it on his website. And she was concerned that that other person wasn't honoring any copyright, like proper sourcing and stuff. And so she just brought her site down, and it hasn't come back up, which is unfortunate. Now I can share information that I've gotten from his site, if people would like to see some of it. And I have done that in the past, just in kind, to let them know that it's his work, not mine. You know what I mean? But I definitely don't have any special permission to do that from his daughter or the family, which, is very unfortunate but he worked in NASA. And one thing I did observe, that he took a lot of his work that he knew that he was doing in the lab, and I think and he's given presentations in Germany. He's done whatever that conference, the Electric Universe conference, he's presented there before. So that's a good source. If you really want to find out what he has to say, I would say go to the thunderbolts.info or the Thunderbolts Project YouTube, and then just watch, search his name and watch his YouTube videos. They're very, very enlightening. I
think I mentioned this before, that when I gave maybe my first presentation to the NPS at the time, many years ago, he was in attendance, and he said, I was quite heterodox, I suppose, but he said he agreed with most of what I said. So, I think we were looking at things maybe from a different viewpoint, but there wasn't a major divergence in results. So Jim, anything else you'd like to say to Harvey, or generally, before we?
Well, thanks for the presentation. I'm good.
And thank you very much for your contribution as ever.
So the main difference I would just see is that in relativity, it doesn't matter what the velocity, and they say you can not go beyond the speed of light. And I think that's very odd, because people used to think you couldn't go beyond the sound barrier. But so here's the catch, or the key. if we think in a paradigm of the current fields and the local systems that we have to deal with, maybe we can't get the fields to move faster than C, because the fields in our reference frame from the sources we're using, which are these big, massive collider things, linear accelerators and stuff, they're operating, and we're locked into this 90-degree angle paradigm for observing and emitting signals and having things travel through space. And we think that's the limit. So actually the equipment's limiting our thinking, not us limiting the thinking, because, so I just think that in the very beginning epoch of cosmology, if you want to call it, the energy or the origin of the physical matter that we have, and this is not necessarily just philosophical. I think it's actually was at much greater speeds, the energy itself that created the matter or made the matter when the matter was being formed was going at a lot faster than what we would call C, the limiting distance. And it has to do with this 90-degree angle that we keep putting in our mind, and we have that C is the ultimate velocity of the speed of light or energy or quanta or whatever you want to call it. And I think that's just because someone says it is, that doesn't necessarily make it so. And so how can we have, this is like a muon thought experiment. Chat GTP, we just destroyed it. Asking Chat GTP about muons, I said, okay, if you take the lifetime of a muon, now, of course, it may be in a fixed reference frame and it's sitting there, and they're popping out from some experiment and they have a normal lifetime, the average. Well, if you take that delta T, and then you know that from a fixed frame source, and then all of a sudden these things are being created in the upper atmosphere, they're hitting our atmosphere, and boom, you have these muons coming to the Earth. Let's just say it's at 10,000 meters or higher, or 15,000 meters. If you take the delta distance, because we know they make it to the Earth, some of them go deep into the Earth, right? They penetrate very deeply. If you take the distance X over T, you get a velocity that's like 20 something or 70 something. It depends on what your altitude is or whatever. You get something that's 70 times the velocity of the speed of light. And you're going, no, that can't be right. But why can't that be right? Because the source is extra galactic. I mean, it's the source is, we don't, the source is out there. It may be coming, that particular radiation might be coming from the original field that made everything, and everything's pretty well interconnected. So anyway, I'm kind of.
I think the common thing we hear when we pose these matters with regard to galactic distances where the speed of light is dynamically exceeded, they say, "Oh, but you can't send any information by these means." It's a sort of a quick out, But that's the case. By the way, this other man or lady, I'm not sure, it just says that the light clock seems to be an early reference to this Lawrence S. Lerner, 1996. He seems to be earliest. Maybe Wiki said that. We might like to check that. Yeah. What is it's something? Is this a German term or something? User verbs on Steemit has some of Dowdy's site in a post. Also, there's beyond mainstream. Some of Dowdy's material there.
Oh, okay, cool.
Yeah. Okay. So that's useful for you as well. Now I see Dennis Allen is here, and I'm wondering, Denny, if you'd care to come in for a moment just to give us maybe your response to any of these, good, bad, or indifferent, or if you'd like to suggest that we look at anything further or look at other things than probably what we have concentrated on in the last hour.
Well, I like Dowdy's approach. whenever I hear about light clocks and so on, which up until now, something in my head says, "Wait a minute here. There's something funny going on here. I don't know if I can believe this or not." But I don't get that feeling with Dowdy's work. He breaks it down to little steps that you can follow. There isn't something magical going on. There isn't. It makes sense. I'm very impressed.
Okay, well, it's valuable to get some feedback there because
Thank you.
I don't know if we have any clear as clear as that exposition from many of us in the CNPS as to whether we like Dowdy's work or we don't, or we think there's something in it. We're all maybe a bit on the fence, but it's useful that you, Harvey, have gone into it, and you're continuing to go into it, and you say you have a lot to do. So we're hoping that maybe a lot more information will come out of your studies, and perhaps in the future you'll be able to come back to this and give us more enlightenment.
Well, to me, one thing that I think would be the experiment to really, it's already being done. Have you heard of Super Keo Commandi? It's an experiment in Japan that they buried it like 1 kilometer or whatever under the solid rock in a mountain. And it's the size of a football field. And they put this gallium arsenide type liquid distilled water mixture. And they have like 10,000 or so of these hand formed by very excellent artisan photo detectors, right? That are very, very sensitive. And they surround this water chamber with these photo detectors. And what happens, lo and behold, the sun shoots out neutrons. And of course, neutrons can travel very far if they're high energy, right, or whatever. They go through some kind of process where it hits the gallium because it makes it denser in what they call impact parameter density or whatever. And then 2 reactions happen. One reaction sends another reaction, which causes another atom in the water to have another reaction. So you get 2 reactions, which are 2 light sources. Boop, 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 boop. And that's what they're doing. And of course, the water slows everything down by 50% or 75%. It slows it down by 25%. So they get these cones that a supercomputer picks up these patterns on the walls, of the detectors. But it's 2 signals. It's boop, boop. And the cool part is if someone could go through the math or the geometry and simplify it and say, let's get rid of relativity. We just want to know exactly in real time, what did the supercomputers say? They detected the signals. Of course, they're having to go from some wires from the detector all the way to a computer. And then guess what they're probably doing? Putting the relativistic correction in the data, right? So that everything works out so that Einstein and all that stuff, math, is not violated. You're not violating any of those rules. But if you just had raw data on exactly when did each one in real time synchronize, do you know what I mean? Real time, these things got these signals, like these 2 birth and death signal, I would call them, making this light cone called Cherenkov radiation, right? You know what makes that Bremsstrahlung radiation or whatever patterns. I think it would be surprised that you would think that some of these extraterrestrial sources of energy are probably moving at velocities that we can't even think of.
So in other words, not just slightly exceeding the speed of light.
No.
It could be orders of magnitude, yes.
It's orders of magnitude. That's what I'm thinking. But I don't know the raw data. I don't know. I'm not that kind of a person that can go through, like that kind of information. And then I don't know what data they're publishing. Is it really raw data? where there's a time clock that says, okay, they're all synchronized on certain on a real time clock, like we receive, and then the wire length is taken into account so they know the propagation of the signal, So in other words, yeah, you got the picture. Unless we actually can get raw data to work with, it's going to be hard to unravel all this stuff.
Yeah, well, it is a fundamental point that it's surprising, maybe to some extent, that we don't have a strong view one way or the other, or there's there's no definitive information.
So one thing I can say that I think might have been a source for Dowdy's work, but this is speculation, just remember. So don't quote me, it's my speculation. I'm starting to read that Ritz ballistic theory.
Right.
And there was a book recently published. It's like 450 pages big, and it's a century after the fact. Like over 100 years later, these professors got together and spent a lot of time to say, what did Ritz ballistic theory say? So Ritz believed in these little bullets, and I'm seeing, and I've only gone through 100 pages of it so far, so that's as far as I've gone, and I'm seeing some things that are similar to what Dowdy is saying. Instead of like little bullets flying in and out of a particle or whatever, I think it's, I got to be careful here. I see some of the things like are similar, that's all. But it's definitely, I think Dowdy does everything from an energy perspective, like radar, some kind of radiation EM wave type perspective. In other words, there's no, as far as I can tell, there's no medium.
So does Dowdy say anything about Ritz? Like his own view of it?
Maybe I need to look at his references, but I'm not sure. But I'll give you one example. In Ritz's ballistic theory, he has these things called rheons. And so they're always going out of a particle, but anti-rheons are coming in, and you got all this. So that's kind of like his ether. And I think it's more of a field. If you just converted that to a field, it would be better. And so he says that what happens is like, say, on a mirror reflection, you have this energy coming in, but it's really rheons exciting the surface of the mirror, and they're re-emitting the what that he doesn't believe in photons, but they're re-emitting what we would call the light signal. So that's one reason why in Dr. Dowdy's theory, I think it's V plus C to the mirror, but when it reflects off the mirror, if the mirror is fixed, it's C. So it's V plus C, C. Because the original source is going through the mirror and keeps on going, and it's exciting the matrix of the atoms in the mirror, which are now reflecting or emitting its own source. That's called the secondary source. There's the primary source and the secondary source. That's similar.
So, Danny, anything else before we move on?
No, I have nothing to say except that I'm very impressed about it. It's very impressive.
Okay, well, that in itself is a valuable response, because we'd like to know.
Thank you.
So thanks very much, Danny. Thank you.
Ian, you're welcome to post the material too if they want to. If someone on the website wants to download it, they're welcome to have the.
Do you mean the slides?
Yeah, the slides.
Yeah. Well, that's actually very valuable, Harvey. Thank you for that. As you do know, this will be available as a recording immediately after we've terminated. Okay. Now, you can always reduce the speed and stop in various places if you're listening to it. But if anybody wants the slides and you request them, I'll take up your kind offer and I'll pass them on. So that applies to everybody. So I'm just wondering, Cornelius, do you have any? You put a comment earlier in the main chat. I'm just wondering if you have anything you want to say briefly, Cornelius.
Yeah, I think the comment you're referring to in the main chat was probably talking about the light triangle, where the light was actually moving in 2 dimensions instead of 3, instead of single dimension. Because I think somebody else was mentioning that in Einstein's original discussion, he was moving along a straight line, and the observer was on the same straight line path to the thought experiment. When you start using a light triangle in that, anytime you expand one side of the triangle at a linear speed, then the third side, hypotenuse, is going to expand in size at a logarithmic speed, because you're actually extending the length of that side. It's kind of like looking at a falling ladder on a wall or something. So you're not really talking about a constant distance then, because the distance is changing, which means that there's an acceleration involved that the light has to deal with as it goes through the path. So that it kind of makes that difficult to compute that way. If you understand what I'm saying, if you're starting in a straight line, they're both equal. If you're not moving, you got one vertical line, and that hypotenuse is going to lengthen as you turn it. Even though the base is moving at changing in linear distance, the hypotenuse is going to be changing at an accelerated rate.
And were you suggesting it was a bit odd because SRT was endeavoring to deal with all these things, and yet it doesn't really cover acceleration?
Exactly, and that's why I'm saying that particular type of example, you can't really get a good feel for true SRT. SRT, well, one of the things it says is that light is a constant speed, and that's actually just a postulate within SRT that Einstein uses as a basis for the math. It's an assumption that's made that light is constant, and therefore all the calculations are done based on that. So therefore you have to change distances, you have to change clocks to make the calculations work. It was a chosen path, and it may not have been the most clean and complete chosen path. I don't think it was ever really brought out to its full potential, but when you go to the full potential, you have to go to include acceleration, you have to include gravity, and he's going to that with general relativity. I'm not by any means an Einstein expert, and I don't really have much background in the mathematics that way, so I'm not really qualified to speak in that direction. But that's my understanding, is that it's not really a complete theory yet, and it may be in the wrong direction even. But as far as the talk goes here, there was some mention of faster than the speed of light, and with light being considered to be a transverse wave, it's dependent on the media it's moving through. But in my view, the media is a nonlinear elastic bond continuum, and so there's really, it's like a solid. And solid can carry both longitudinal and transverse waves. And in most solids, the longitudinal wave does exceed the velocity of the transverse wave most frequently, if not always. I'm not sure about the not always statement there, but and so it can be exceeded by quite a bit. The thing is that we're not aware or able to detect at this point anything that's moving through space as a longitudinal wave. What we detect is the electromagnetic transverse waves. I believe that the longitudinal wave is the key to it, and those are the waves that are responsible for mass and gravity.
I agree.
Harvey.
Yes,
Another
I have a
topic.
We see things like that in an exploding black hole, and that they see jets coming out of that black hole that far exceed the speed of light. But what's really happening, in my view, is the jets aren't really coming out of the black hole as much as they're taking the overall gravitational field of the black hole, and there's an interference pattern that happens as it explodes that causes the light emitting particles and stuff to be generated along that jet path. So they're actually being generated by the interference patterns of the gravity waves, which could be then, would then appear to be material actually exceeding the speed of light rather than actually just material being generated
No,
by
no,
gravitational interference. That's just a thought on that subject. It's not by any
Okay,
means,
no, that's useful for further.
that does bring up something. I remember on Dr. Dowdy, he mentioned black holes, and basically he said like the galactic center. He said he took images of the real positions of the stars at the center of our galaxy, and basically he showed their pattern over time that we've recorded, and there's no Einstein lensing going on. So he proposed that really what's at the center of the galaxy, and this would have to do with the electric universe theory, that the current, the electromagnetic fields, the fields that are going from the spiral arms into the center of the galaxy are coming back out through the poles, right, up and down, and that's what's causing the motion of these stars that are in the center. And you don't see mass because it's not mass, it's fields, and it's maybe plasma ions and electrons, that material that's being ejected from the north and the south of these huge disks. And so my idea that this is not Dowdy, but that was Dowdy, what I showed you. So he said there was no evidence of gravitational lensing. So I think he was aligned with the electric universe type concepts of plasma. But I think the prime mover, the source of all the energy that we see, is what's missing. What's missing? You mentioned the gravitational fields, right? Is it Cornelis?
yes.
Okay. Hey, yeah. The gravitational field, to me, what it is it's what we would call destructive interference, and particles are constructive interference, constructive, and destructive interference has a negative connotation in our language. It means that there's nothing there. It's fields that oppose each other perfectly. And when I say oppose, I mean like if it's spherical or horizontal versus vertical polarization, those kind of. They don't destroy. What they do is if you have pairs of them, they can counter each other in such a way that the energy can still be flowing through in both directions. And what will happen to me is that's called destructive interference, but it's actually the driver of the gravity field. So the gravity field is, to me, destructive interference of the particle creation, and the particle itself. The reason why you have torque inside the particle and you have spin and all those things is because the energy that made everything in the very beginning was moving at much faster than the speed of light. It was basically an inward focus of overlapping energies that as it was coming in one way, it was going in the other way, but they were complementary waves in such a way that what was left is the focus is what we call the particles, electrons and protons. And it's my idea. Other people in the electric universe are thinking that a neutron is nothing but a compressed hydrogen atom. It's so compressed that it basically attracts the proton, because the electron is a sphere on the outside. The proton is here, and it's attracted to the proton inside while the electron's repelling it. So that's why you have a compressed hydrogen atom making a neutron, and it's stable as long as it's inside an atom, and then you have the particle building of atoms of the atom. And I believe that the original, the most like abundant thing in the space that I know of is like oxygen and hydrogen. So it's mainly water. So the water molecule was a sweet spot in this cosmological event. And what's left over is the gravitational field. And the gravitational field is still flowing through everything. And so basically the particle itself is just the focus of constructive interference, and the gravity is the destructive interference. And that's why in our experiments, when we take and we do phase shifting of these different paths, and you can say the probability of finding something is in the A position or the B position is either 100% this way or 100% this way or some different count in between. And the reason why is because we're not taking into account the gravity field, that if it's zero here, it's still gravity. The energy is still flowing. It's destructive.
Harvey, we are running a bit out of time.
I diverged.
Let's bring Harry in. No, that's fine. We can give you a little opportunity to summarize at the very end. So before bringing, by the way, should we be saying Cornelis or Cornelis? It doesn't matter.
Cornelis is good. Yeah.
Oh, Cornelis. That sounds cool.
I think I've been saying it wrong for the last 10 years.
I think I'm just going to cap off what Harvey said. I'm not going to. I have my own theories, and I'm not going to by any means go into them because they're going to take.
No, we won't.
It's totally off. But
we'll
basically,
we'll come back to this.
So what Dowdy said about extinction theory, and that to me, things go in and out of particles. They change speed as they go in and out. Dowdy's got some good points. A lot of what I see is it depends on what you see. How extensive is the particle? When are you really entering and exiting the particle? And that.
So if we can leave it at that for a moment.
So I'm going to just leave it.
Thanks very much. I'll leave it at that for the moment.
Okay, Harry. Who
now, Harry. Harry is there, I see, and as we said earlier on, Harvey himself said that if Harry wants to come in and clarify anything that he says, he's quite happy to say that, and that's an invitation, of course. But I'd be happy to get Harry's response, to Dowdy's ideas. If he has any view, positive or negative, or if he believe some of it, or if Harry has some questions of it. I'd value your response, Harry, to what Harvey's been saying and Dowdy. We can't hear you at the moment. Your mic is unmute. Can see you perfectly, but only got a little bit of breaking up sound there. So I'm a little worried about that. As you said in a recent email, you think your computer doesn't like StreamYard. I don't know if it's as simple as that, but you seem to be having problems all right, unfortunately. Unless you'd like to put a comment in the private chat, just
well, I'm not real. I don't want to pass a judgment on Dowdy because I don't really have any judgment on Dowdy. Are you copying me all right?
We can hear you now.
We can hear you just about.
Yeah,
if you speak slowly, maybe.
My computer doesn't like StreamYard. Okay, my comment is the light clock was Lewis and Tolman. On.
I can't hear you.
No, you're breaking up. It was fine for the moment there. You said the light clock?
The light clock is Lewis and Tolman,
1909. Okay, a lot earlier than the other reference we had here from the 1990s. Okay, have you any general view on the extinction shift principle? We needn't even personalize it. I mean, do you think that something is a useful concept?
Okay, the light clock 9. Theory of relativity and non-Newtonian mechanics.
Okay. We're not hearing you actually, so I don't think we're going to be able to get very far here. But I was just wondering, one might argue that the idea of an extinction shift has certain other elements. I mean, maybe the Huygens principle, of re-emission. Is important, and I've looked at things like stellar aberration, where there seems to be,
depends on whether space is a substance or space is a non-substance. That's probably
better that you've switched off your video, so the complete bandwidth is now relegated to the audio. But Yeah. Okay. So is that the only point you wanted to make, Harry, or did you want to make? We have we're running out of time now, but we have a couple of more minutes. And I see Harvey's daughter, I assume, is she's been trying to get our attention, which is fine. A little light amusement place. Is that everything, Harry?
It's not a bandwidth issue. It has to do with my connection to the StreamYard.
Yeah. Well, it's not really the place to do it, but
Lewis
that sounds wrong to me. I mean,
Lewis and Tolman,
connection to any
1909.
application. I don't see how StreamYard could be the problem. We might have to do some tests, using some other platforms to see can you get through more satisfactorily. But I mean, that's perhaps for another day. I have two more comments.
Lewis and Tolman, 1909.
Okay.
Oops. That's probably the Lewis who actually brought in this whole energy and mass transformation, and Tolman, of course, is well known. He worked with people like Hubble and so on. Okay. Well, I'm sorry. I mean, it's a good sign in a way when we have to cut everything off and allow. You've got two children there, which is excellent, and they're looking forward. They look very sweet. They're not twins. They look about the same age. No,
right. They're sisters.
Okay. But I'm always sorry to have to curtail the conversation. But on the other hand, it means that it's been quite stimulating, and we haven't been sort of waiting for people to respond. We all want to make points, and Harvey has sort of stimulated a lot of two darling girls. Great, Harvey.
Yeah. Okay, so do you want me to summarize?
Yeah, would you summarize briefly, and then we'll close the meeting. You have a minute or two, so that's great. Thank you.
Well,
I'd like for a moment.
I'd like to. I appreciate the opportunity to just show a brief description of what I believe Dr. Dowdy was trying to communicate on extinction shift principle from a relative time shift perspective, and showing that this is me talking now, that if experiments show that the special relativity time dilation formula works under restricted conditions, I think Dr. Dowdy shows that it's actually from moving sources that are actually creating the signals that we're receiving. And yes, that it's in a restrictive sense that formula works, and it's called transverse relative time shift, and as opposed to time dilation. In other words, clocks are actually slowing down somewhere. Moving clocks are changing their rates, which he's just showing that basically the time signal delays are natural, and it's which includes the source of the velocity that must be included in the equation. And if you think about it, if the time is changing, you can take if your measured time of what you expect is, you can calculate it, and you can expect this time from this formulation. You can actually infer what the original velocity was, but without that knowledge, it's difficult to show or prove such thing. So anyway, you can also now see that if your time increment that you measure is different because the velocity of the source is one thing, then you can say, oh, well, I guess then my inferred distances traveled might be different. But that's not necessarily the case. The source is actually moving at a specific velocity. So, and we can tell in the examples that I provided exactly where that position is of the source at a given time. So anyway, I'm just appreciate the time allotted for me, and hopefully continue sometime in the future on this discussion or other discussions. Thank you, Ian.
Well, thank you very much, Harvey. And actually, your girls were probably told by you that this thing will be over in 2 hours, so they're very accurate timekeepers, because it's just expired, or it's just expiring now.
Okay, appreciate y'all. Thank you very much.
Well, thank you very much for taking the trouble to give us this talk, and with all the complicated diagrams there, and going through it in detail and so on. And I agree with you. This is only the beginning, really, of our analysis of this subject, and we'll come back to it, and we'll discuss it in much more detail. And it was actually a very welcome break from some of the other ideas which we were looking at, to get back maybe more fundamentally to SRT vis-a-vis other ideas such as
Okay.
transverse time.
Okay.
Relative
Yes.
time
Okay.
shift. So thanks again, and we'll let you go. And
Okay. Thank you.
it's only midday. Goodbye again. Thank you very much. So bye now. So it's my duty now. I don't say pleasant duty. Always sorry to finish the conversation, but it's been a successful meeting, I think, today again. And we look forward to your participation. Thank you all very much for your participation. 7 new comments have come in on the social media, which I think we don't have time really to look at, but it means you're all thinking ahead of the subject. I think one of the guys here, Andrew, is an ex-NASA man as well. So thank you for all those comments. And keep an eye on the system. We have a sort of a roster at the moment, and I think Denny might be back to us in the not too distant future. So just keep an eye on the announcements. And I'd like to thank all of you again for your participation, and thank you in the green room for coming in and making specific comments on Harvey's presentation. We look forward to seeing you again. It'll no doubt be in 2 weeks' time, same place. And so I'll wish you all a very good day, whatever part of the globe you're in. I shall end the broadcast now, and thank you once again. Thank you, Harvey. Thank you, everybody.